In this video, we will go through the topics that you guys asked that we go through as a last-minute review before the AP test. So one of those topics is combustion analysis, and if you remember, combustion analysis is where a combustion reaction takes place. We get CO2 and water, and from that we can backtrack to figure out the moles of carbon, the moles of hydrogen, and maybe even the moles of oxygen or something else, and we can get the empirical formula and then the molecular formula of our hydrocarbon. So in this example, we have a flammable hydrocarbon that contains carbon, hydrogen, nitrogen, and oxygen. So this generic formula looks like C some number, H some number, O some number, and N some number. And it'll combust, so it'll react with oxygen, most likely under heat. And when we take 0.487 grams of this hydrocarbon and we combust it, we get 1.321 grams of CO2 plus 0.325 grams of water. And then we also get 0.0421 grams of nitrogen. And this is like an old FRQ question. What we're trying to do is figure out the mass of carbon and hydrogen present in the original sample. So the way we will do this is we will say, okay, in A, we'll take 1.321 grams of CO2, and we'll say that there are 44.01 grams of CO2 in 1 mole of CO2. In 1 mole of CO2, there is 1 mole of C, and then in 1 mole of C, there's 12.01 grams of C. And when you plug that into your calculator, we get 0.360 grams of carbon. And then we also need to do water. We are given 0.325 grams of water. There are 18.02 grams of water for every 1 mole of water. And in 1 mole of water, there is 2 moles of H, and in 1 mole of H there is 1.01 grams of H. And so from this we get 0.0364 grams of H. So I've answered question A. And they want us to determine the mass of oxygen in our sample for B. Well, our sample, we've got this whole sample, which is 0.487 grams. And I know carbon already, I know hydrogen, I just need to get oxygen. But the problem is I can't just subtract right away because I don't know nitrogen. Right now that is unknown. So what I need to do is I just need to do this process again. And in the question we are given 0.0421 grams of nitrogen, and there are 28.02 grams of nitrogen for every 1 mole of nitrogen. In 1 mole of nitrogen there is 2 moles of just N, and in 1 mole of N there are 14.01 grams of N. And so what I get is I get 0.0421 grams of just N. And you may say, well, that's the same thing that I started with. And the reason why I did this is that in some combustion reactions, we don't just get N2, we might get something like NO2. So we'd really need to go through this process a long way to figure out the grams of N. But here, we didn't have to do that technically. And so what I'm going to do is I'm going to take 0.487 grams of our sample. We will subtract 0.360 grams of C minus 0.0364 grams of H minus 0.0421 grams of N. And when I do that, what's left over is 0.0485 grams of just O. And so I have answered question B. Now what they want us to do is they want us to get the empirical formula for our hydrocarbon, and so that's just percent to mass, mass to moles, divide by small, multiply until whole. And we don't have any percent, so we're at the step of mass to moles. So I'll take, and I need to write kind of small here because to save paper, I've kind of made the lines not as large as I would normally done. So we'll take 0.360 grams of C. There's 12.01 grams of C for every 1 mole of C, and when I do that, I get 0.0300 moles of C. And then I'll take 0.0364 grams of H. There's 1.01 gram of H for every 1 mole of H, and when I do that, I get 0.0360 moles of H. I've got 0.0421 grams of N. There's 14.01 grams of N for every 1 mole of N. So I get 0.00300 moles of N. And then I've got 0.0485 grams of O. There's 16.00 grams of O for every 1 mole of O. And that gives me 0.00300. Oh, I looked at that wrong. 303 moles of O. Now what we're going to do, we've done mass to moles, we'll divide by the smallest one, and we've got to make sure we're clear on our decimal points that the smallest one is 0.003. And so what I get is I get 10 for the carbons, 12 for the hydrogens, 1-ish for the nitrogens, and 1 for the oxygens. And so my empirical formula is C10H12 and then NO. And when you go through and you get the molar mass, you'll find out that this is 162.23 grams per mole. And I've gotten the empirical formula, but they asked for the molecular formula. So for part D, what I have to do is I've got to realize that they've told me that the molar mass of the actual formula or of the molecular formula is between 300 and 350. So the only way that 162 gets in that range is that we multiply it by 2. And so my molecular formula is C20H24 into O2. Okay, so that is how you do combustion analysis. Another topic that we probably need to go over is collection of gas over water. So collection of gas over water is when you have this setup where we did it in lab where we had an Erlenmeyer, but it was really a sidearm flask, and we had a piece of tubing, and gas traveled through the tubing and was collected into an upside down graduated cylinder. And what we could do is we could read, and it was in a sink, and we could read the volume of the gas. The problem with that is that there is humidity that is influencing the pressure, and so we don't care about any of that. So let's go through this process. It should be pretty straightforward, but most students would actually get this wrong on the AP chemistry test because they would just forget this the humidity part. So what we have is we have a sample of hydrogen peroxide, and if it's an aqueous solution, that means most of it is water, not all of it is hydrogen peroxide, and so it's 6.951 grams. The H2O2 solution decomposes completely, and this is the reaction above. We get some oxygen gas collected in an inverted graduated tube over water at 23.4 degrees Celsius, and it has a volume of 182.4 milliliters, when the water levels inside and outside the tube are the same. The pressure in the lab is 762.6 torr, and the vapor pressure of water at 23.4 degrees Celsius is 21.6 torr. So what they ask in A is they say, what is the pressure of just oxygen? And they want it in torr. Well, if you remember this formula, that the total pressure is going to be equal to the pressure of the gas, and that gas for us is oxygen. That's the oxygen that we care about, plus the water vapor. And so the question gives us that the total pressure in the lab was 762.6 torr. That equals the oxygen gas plus the humidity, and they tell us that the humidity has a pressure of 21.6 torr. So when I subtract that, P of oxygen, the pressure of oxygen, is 741 torr. Okay, so A is done. In B, it says calculate the moles of oxygen produced in the reaction. Well, when you're dealing with gases and you need to get moles, a good way to do that would be PV equals nRT. And depending on what you use for your gas constant R, you might have to convert your pressure, because what I know is that we have 0.18, we had 182.4 milliliters, so that's 0.1824 liters. We want to know the moles of oxygen. The only R that I ever use is 0.0821 ATMs times liters divided by moles times Kelvin, which tells me that I need to get my pressure into torr, or excuse me, from torr to atmospheres. When I add 273 to the degree Celsius, I get 296.4 Kelvin. And so what I'm going to do is I'm just going to save some space here, and I'm going to say there's 760 torr for every 1 ATM. And what this does for me is I get 0.975 ATMs. And so my moles of oxygen are 7.31 times 10 to the minus third moles. Okay, so B is now done. Now what they ask is calculate the mass in grams of H2O2 that has decomposed. So notice how these AP chemistry free response questions kind of work, is that A will feed into B, which commonly feeds into C, which will probably feed into D, and so on and so forth. So what we want to realize is that we just solved for an amount of oxygen. The question now asks for amount of H2O2, so what that means is we're going to need a mole bridge over there. And so in C, what we're going to do is we're going to take 0.00731, or 7.31 times 10 to the minus third moles of oxygen, and we'll just look up at our reaction. There's 1 mole of oxygen for every 2 moles of H2O2. A lot of students would stop here, but they ask for grams, so we need to go to grams. In 1 mole of H2O2, there are 34.02 of H2O2, and so when I math that out, I get 0.497 grams of H2O2. Okay, in part D, they just want the percent by mass in the original sample. So remember, like I said at the beginning, the sample is mainly water, okay, because it's aqueous. So what we need to do is to get a mass percent, we want specifically the percent of H2O2. So what we'll do is we'll take mass of H2O2 divided by total mass. We'll times it by 100, and that will give us our mass percent of H2O2. And so that will equal 0.497 grams of H2O2. The total sample was 6.951 grams. Times it by 100. We're not expecting a whole bunch, and actually what we get is 7.15%. Okay, so question D is done. In the last one, what they want is the oxidation numbers of oxygen in H2O2. If you remember, oxygen is almost always -2 unless it's with O2, because then it's 0. So I guess I just answered that question. And one exception is hydrogen peroxide, and it has to do with the Lewis structure. So the Lewis structure of hydrogen peroxide looks like this. And what you realize is that oxygen can only steal electrons from their hydrogens. Oxygen cannot steal electrons from each other. So an easy way to do this is to just remember that hydrogen is almost always +1. So if you know that hydrogen is +1, then oxygen has to be -1, and that is the oxidation number of hydrogen or oxygen in hydrogen peroxide. Okay, so what I want to talk about is testing the different types of solids. I'm going to focus on really only 3 types of solids, and that's going to be covalent, metallic, and ionic. And let me just go through their properties because that'll help you figure out how you'll figure out what type of solid based on an experiment. This is very similar to an experiment we did back in December where you had a whole bunch of little plastic cups, different solids, and you had a conductivity tester that would beep at you if it was conducting electricity. So let's first focus on the solid phase. Metals or metallic bonds, they always conduct electricity as solids. That's because they have a sea of delocalized electrons, so they have electrons buzzing around all the time, so they're able to conduct electricity. So if something conducts electricity in the solid phase, that means it's going to be a metal. Covalent and ionic do not conduct electricity, okay? So do not or don't conduct as solid, okay? However, ionic, if we dissolve it in water, some of it will dissolve at least a little bit. The KSP would have to tell you exactly how much dissolves. We're not worried about that at this moment. But this would conduct electricity as aqueous. And I don't know if this would show up, but it also conducts as a liquid too, but that's very impractical because most ionic compounds have high melting points. Okay, and then covalent never conducts. However, it can dissolve in water, so polar compounds will dissolve in water. But nonpolar will not dissolve. So what this question says is that we have 3 substances, X, Y, and Z, and they say that they were studied in the laboratory and the data was collected based on the data, which of the following shows the type of bonding in each substance. So what I'm going to do is I'm going to strictly look at if there's any metals, because metals are the only thing that we need to worry about conducting as a solid. And so what we see is that conductivity in solid phase, and X and Z, those do not, so those must not be metals. But Y does, so Y must be a metal. Compound Z conducts electricity in the liquid phase when it's melted, so it must be ionic. And compound X never conducts, and so it must be some sort of covalent compound. And so I think the only answer that matches that would be part D. Okay? It's very common for a question like this to show up on the AP test. Now, what people asked about is how do you do pH calculations kind of without a calculator, just estimating? Okay, so what we need to make sure we remember is that pH equals the minus log of H plus, okay? And so if I'm given H plus, all I would need to do is take the negative log, and here we have 1 times 10 to the minus 8. And since the base of our scientific notation is 1, that means that this pH will be 8, and that's above 7, so it's slightly basic. And so E would be our answer there. Most people don't have issues with that. But what do you do if we have the pH of this? Well, first, you realize that they don't give us the Ka value, so this must be a strong acid. I would not worry about it in its decimal form. I would convert it to its scientific notation, 3 times 10 to the minus 4. And so the pH equals the minus log of H plus. Strong acids dissociate 100%, so this is really the concentration of H plus and of nitrate. So we want to take the pH equals the minus log of 3 times 10 to the minus 4. So what I know is that since the base is not 1, that the pH is going to be a little bit less than 4. And if you remember, if the base is at 3, it's pretty much going to be a 0.5. So we know it's going to be less than 4, so pH is equal to 3 point something, and that if the base is 3, then it'll be 3.5, and I'm going to say ish, and we specifically get 3.52. Here we're asked to get the pH of potassium hydroxide, the concentration of 0.006, so this is 6 times 10 to the minus third. Well, this, because it's hydroxide, I need to do the pOH. pOH equals minus log of hydroxide, and so pOH equals minus log of 6 times 10 to the minus third. And so what that means is that this pOH is going to be 2 point something-ish, and probably that's 2.22. Some people are going to select that, but remember that pH plus pOH equals 14, and I just got the pOH, and I'm asked to get the pH, so I'm going to take 14 minus 2 point something-ish, and that's going to give me 11 point something-ish, and there's only one answer that matches that. So you got to be comfortable not ever getting the exact answer, but saying that it must be A in this case, because that's the only one that would be close enough. Now, if they give you multiple Ks, if they give you Ks, first of all, if you are given Ka, it must be a weak acid. Okay, it must be weak for whatever it is. But if they give you multiple Ks, remember, the second and third Ks mathematically are insignificant. When we did the acid and base unit, we proved that they would give us the same answer, so we never really have to worry about the second or third Kas. But we have H2S, so H2S plus HOH, we will get H3O plus 1. If I can get the concentration of this guy, then I can take the negative log, and that'll be the pH plus HS minus 1. And so we have 0.02 minus X, 0.02 minus X, 0, 0 plus X, X, and X, because this is a rice table. And so my Ka expression equals H3O plus 1 times HS minus 1 divided by H2S equals X squared divided by 0.02 minus X. That all equals 1.1 times 10 to the minus 7. And this one you probably need a calculator. You could estimate, but here's what I'm going to do is I'm going to try to do it without a calculator. First of all, 5% rule. We don't know, we don't need to know what that, or we can cross out that X. And I'm going to multiply my denominator by 1.1 times 10 to the minus 7. And that's some hard math, but let me show you how to do it kind of mental math. We're going to take 2 times 10 to the minus 2 times 1.1 times 10 to the minus 7. And what we should end up with is 2.2 times 10 to the minus 9 equals X squared. We take the square root. And what we're going to get is a number that maybe you could estimate, maybe you wouldn't, but we're going to get about 4-ish times 10 to the minus 5. And when I take the negative log of that, I'm going to get 4 point something-ish. And if you look at the answer choices, we only get B as a possible answer, so it must be B. In 5, and I'm going to erase the rest of this to give myself some room. In 5, what we're given is we are given a salt, okay? And what we need to do is we've got to react it with water to get the pH. So what I'm going to do is I'm going to take NaNO2 plus HOH just in a double replacement reaction. I'm going to get NaOH, that's a strong base, plus HNO2, and that is a weak acid. I know it's a weak acid, one, because I have my weak acids memorized, but if you don't, they gave us a K value, so it must be a weak acid. And so I'm going to set up a rice table. 0.50 minus X, 0.50 minus X, that's a pure liquid, so not included. 0, 0 plus x, and plus x, and so I get x and x. So I'm going to be a little bit lazy here just to save time, because this video will probably end up being a little bit long. I'm going to say x squared divided by 0.5 minus x equals not 4.5 times 10 to the minus 4. A lot of people would do that, but we need KB because we produce hydroxide. So Ka times Kb equals Kw. Ka is 4.5 times 10 to the minus 4. Kb is unknown right now, and Kw is 1 times 10 to the minus 14. And so when you do this, Kb, I'm just going to use a calculator on this one, but you should be able to kind of estimate it. We get 2.22 times 10 to the minus 11. And so 2.22 times 10 to the minus 11 is going to go there. I can use the 5% rule to get rid of minus x. And what I'm going to do is I'm going to take 0.5 times 2.22 times 10 to the minus 11, which is going to give me 1.11 times 10 to the minus 11, and that equals x squared. I take the square root of each side, and what I'm going to end up with is something, but specifically it's going to be times 10 to the minus 6. I mean, I know the exact answer because I've done it, so I'll give it to you. But even if you didn't get that perfectly, that's no big deal, because we take the negative log of this. It's going to be a little bit less than 6, so it's going to be 5 point something-ish. And notice that's an answer, but that's not our answer, because when I solve for x, x is really hydroxide. So what I need to do is take 14 minus 5-ish, and that gives me 9-ish, which the closest answer would then be D. Okay, so let's do an FRQ. And we've got a lot of different FRQs with acids and bases because that's what you guys asked for. So I'm going to try to go through them quickly. So please feel free to pause videos to make sure that you're solving this on your own, because it doesn't help you entirely to just listen and then not write down and do it on your own, because ultimately you have to be the one to take your AP test on your own. So in A, they asked to write the K value, or the Ka expression, and to calculate its value. So Ka equals H plus H3C5O2, or excuse me, H3C5O3 minus 1 divided by HC3H5O3. And what that is going to equal is, we've got to go through and read some stuff. We get lactic acid, which is 1.66% dissociated in 0.5 molar. So what we know is that essentially we've got a rice table, and I'm going to just set it up, but we don't really need it, but just to organize our thoughts. This is 0.50 minus x, 0.50 minus x, 0, 0, plus x, x, and x. And what I know is that 1.66% of my original dissociates. Well, x is the amount that it's dissociating. And so what I can do is I can take 0.50 times 1.66%, or what I would probably plug into my calculator is times 0.0166, and what I get is I get 8.3 times 10 to the minus third, and that equals x. So remember, we can use the 5% rule and get rid of minus x's and plus x's, like so, but it's not needed here because I just solved for x. So what I'm going to do is I'm going to make this 8.3 times 10 to the minus third times 8.3 times 10 to the minus third divided by 0.50 minus 8.3 times 10 to the minus third. Again, it's not needed to get rid of the x because we know what it is. And so when you do that, you get 1.4 times 10 to the minus fourth. Okay, so we've done A. They want us to calculate the pH. Well, so this was part A, this is part B. pH equals minus log of H plus. So once I know H plus, I can get the pH by just taking the minus log. H plus, according to this rice table, is X. Well, I've already solved for X. So pH equals minus log of 8.3 times 10 to the minus third. And so this is going to be it's going to be a lot lower than 3, but still above 2. And so when I plug it into my calculator, my pH, I get 2.08. Sounds good. Now, C is a problem that a lot of people would mess up on. And so what is going to happen is we already have this original rice table. And what they say in C is that we're going to add some sodium lactate, which will become aqueous. I know it says solid, but it will dissolve because that's what we have in our solution, lactate. And so what happens is that this goes up and we shift left. Because we shift left, we consume H plus, so we're less acidic, and when we're less acidic, the pH increases. That's what we expect. But what they ask for is they say to calculate it, so we actually have to do a number behind it. This is a common ion problem, which is for acids and bases. That is a buffer. You can plug in 0.045 moles divided by 0.25 liters, and you can do it the rice table way, but I think to save some time, I'm going to use Henderson-Hasselbalch, and that is pH equals pKa plus the log of my common ion, which is my conjugate base, divided by just the acid concentration. And that's going to be pH equals pKa. pKa is the negative log of Ka. We had solved for the Ka, that is 1.4 times 10 to the minus 4. So minus log 1.4 times 10 to the minus 4 plus the log of this molarity. Let me plug that in. I got 0.18 molar divided by 0.50 molar. And when I plug this into my calculator, I know I'm expecting a higher pH than 2.08. And actually what I get is I get 3.41. Okay, and that makes sense. That is reasonable. And it's still going to be more acidic because I have more of my acid than I do the conjugate, so it should be lower than the pKa. Okay, let's do titrations. Titrations are something that a lot of students do not feel confident in, and that's okay. They're hard. So do the best that you can with titrations. So what they say in part A is they say write the equilibrium constant expression, and so we would say K is equal to NH4 plus 1 times OH minus divided by NH3. We're going to leave out water because it's a pure liquid. This is going to be a Kb expression, and the reason why is that we've produced hydroxide, so we can use Kb. In part B, they want us to get the pH, so pH equals minus log of H plus, and they don't give me H plus, but they give me hydroxide. So here's how I'm going to do it, is I'm going to find the POH, and so POH equals minus log of 5.6 times 10 to the minus 4. And so I should be able to get the POH a little bit in my head. I'm expecting a little bit less than 3, and so, or a little bit less than 4, and so it's going to be 3 point something, and so my POH is 3.25. Okay, so we've done A, we've done B. They want us to get the value of the base ionization constant, Kb. So what this is going to be, I'm going to kind of just copy this. I'm going to do part C over here, is we know hydroxide, which hydroxide through stoichiometry through your rice table, if I made one, is going to be the same as ammonium, NH4 plus 1. So what I'm going to do is I'm going to say, well, 5.60 times 10 to the minus 4. I'm going to square that because there's two of them, divided by the initial concentration was 0.018. I'm going to subtract 5.6 times 10 to the minus 4. And that's how I'll get KB. KB, when I do that, would be 1.80 times 10 to the minus 5. And you may be saying, Mr. Payne, what are you doing? You did not solve for the pH in part B, and I just realized that. The pH would be 14 minus 3.25, and that would be 10.75. That's my bad. I would not have gotten that point. Okay, part C I've done. Part D, I just need to get the percent ionization, and so for percent dissociation, percent ionization, that would be how much of it breaks apart or how much of it reacts. Well, that is basically going to be X of a rice table over initial times 100. So that's going to be 5.6 times 10 to the minus 4 divided by the initial 0.018 times 100. And so your percent dissociation equals 3.11%. And this makes sense because it's a weak base. Okay, anything with hydroxide you would assume is going to be a strong base, but we don't have hydroxide in the actual formula of our base, so it is a weak base. Now, part E is something that you want to make sure you know how to do because it's probably going to show up. It shows up pretty much every year. And what we have is we've got 20 milliliters of our sample of our base, and we place it in a flask, and we're going to titrate it to the equivalence point, just a normal titration. And we're going to titrate it with a strong acid. We always titrate with something that's strong. Here we need to titrate with an acid because we have a base, so we choose a strong acid like HCl. And its molarity is 0.012 molar. We just need to determine the volume. So what you want to do if it's an acid-base titration, okay, you do MAVA equals MBVB. But to make sure you get the point on the AP test, make sure you write moles of acid equals moles of base, because that is what's true at the equivalence point. And we just plug in what we know. We have 0.018 molar of base. We have 20 milliliters of it. The volume of the acid is what we need to solve for. The molarity of the acid is 0.012 molar. And so VA equals 30 milliliters of acid needed to reach the equivalence point. Okay. Now, when you do redox titrations, which will be later in here, a lot of people do those with MAVA equals MVVB, and that is incorrect. You got to do just basic stoichiometry for those. But let's do a couple more problems with acids and bases before we get to other things. And here what we have is to determine the concentration of HNO2, the student titrates, so we're titrating again, which should make sense because we have a titration curve here. We're going to titrate 100 milliliters of our solution with 0.1 molar of KOH, and we get this reaction here. And what they want is they want us to, using the titration curve, they want us to determine the initial concentration of HNO2 for our solution. So we'll do E part 1 first. Well, if I'm determining a concentration with an acid-base problem, I'm going to use MAVA equals MBVB, and I'm going to say moles of acid equal moles of base. And from the problem, we have 100 milliliters of our acid sample. We are determining the concentration of our acid, so MA is unknown. The molarity of our base is 0.100 molar. They don't give us directly the volume of the base, but what you say is that the equivalence point is where we go vertical on our titration curve, and so that's about at, I don't know, 20-ish milliliters, so I'm just going to say 20. And so when I do the math, I get 0.02 molar of HNO2. Okay, so that is done. Now, they ask us, we need to estimate the pKa of HNO2. Well, let's write on this titration curve because we want to make sure we can read a titration curve because they could give us lots of different things. So, important points. We have our equivalence point. That is MAVA equals MBVB because moles of acid equal moles of base. Okay, that is an important thing. This equivalence point makes a lot of sense because we took a weak acid and we titrated it with a strong base, so our pH at the equivalence point looks to be about 8 or greater than 7. There is the half equivalence point. At the half equivalence point, pH equals pKa because your conjugate base and your acid concentrations are the same, meaning that that fraction there is 1. The log of 1 is 0, and so pH equals pKa. So, before that, we have mainly HA, or our acid. After that, we have mainly A minus, or our conjugate base. If we go past the equivalence point, we have mainly leftover hydroxide. At the specific half equivalence point, HA is equal to A minus. You need to know all of this. Okay, this is what you need to know about a titration curve. So the question says estimate the value of the pKa of our acid. Well, we're just going to go to the half equivalence point because we know pH equals pKa. I'm going to estimate this. That looks to be about, I don't know, 3.3. And they don't ask us to justify, so I'm just going to make sure they know that it's for the pKa of acid. And the reason why is that the pH at the half equivalence point in the titration equals, or the pH at the halfway point of a titration equals the pKa of your acid. 20 is how far you went in your titration. 10 would be your halfway point. So that's how I knew that that was a halfway point. So in part F, they say, during the titration, after you've added 15 milliliters of your base, which species, the acid or its conjugate, is present in a higher concentration in the solution, so we need to justify? Well, let's just find 15 milliliters. That would be about here. And look, that's mainly the conjugate because we've already labeled this as mainly A minus. So what I would say is since, because we have to justify it, 15 milliliters is past the half equivalence point, more than half of our acid has reacted to become NO2 minus 1. Thus, NO2 minus 1 is present at higher concentration. If you are wondering, could you mathematically prove this? Absolutely. This is what I'm highlighting, your buffer region. So you could have used the Henderson-Hasselbalch equation and you could have solved for it. Some people solved, they did pH equals pKa plus log of conjugate base divided by acid. And what they did is they took pH, they subtracted away the pKa, which we could kind of estimate there. Let's just go ahead and do it. The pH at that point is, I'm going to estimate, let's just say 3.7. So the pH 3.7 minus 3.3 gives you about 0.4 equals log of Cb over HA. So to get the inverse of a log, you take 10, not E. If it's just log, you take 10 to the 0.4. And what that gives you is 10 to the 0.4 is we get 2.5 equals conjugate base divided by HA. And since this number is greater than 1, that means your numerator must be larger, which is your conjugate base. Okay, so we mathematically proved it as well. Okay. Let's do some basic equilibrium problems, solving for Rice tables with X and solving for K. So we have this simple synthesis reaction. By the way, I know it's irrelevant, but I'm just going to talk about it because even though it doesn't apply to this, the delta H for this reaction, because we're mainly just forming bonds, should be negative. Okay? Here they asked us to write the expression for our Kp. I'm just going to do it right here, not on the lines, but on your AP test. Please do everything on the lines, unless they ask for you to put it in a box or something. Kp, you've got to use the pressure. So pressure of NH3 squared divided by the pressure of N2 divided by the pressure of H2 cubed. Okay, it's got to be pressures with parentheses. And they say assume that the initial pressures of our gases are 0.411, 0.903, and 0.224. And they say calculate Q. Okay, so Q, I'm going to copy this. Q is the same thing. Okay, Q could just be at any time. So what I need to do is just plug in what I know. NH3 is 0.224. Squared, do not forget to square it. N2 is 0.411. And then H2 is 0.903. And H2 will be cubed, so you got to make sure you cube it. A lot of people would struggle to get this in their calculator to make sure that they got the right answer. You got to make sure you have your denominator with both things in there. So what I typically do is I take 0.411 times 0.903 cubed, and then I take 0.224 squared divided by that answer that I just got from my denominator. And let me plug this in again, 0.224. I get 0.166, that equals Q, so I've done this question. Now I just have to predict the direction that it'll shift, and that's very straightforward because they gave you K. K is 3.1 times 10 to the minus 4, so I've just got to see where Q is. Well, Q is 1.66 times 10 to the minus 1, so it's much bigger. So the reaction, and I know I'm avoiding the lines right now just so I can get it on the screen, the reaction shifts left. What's the reasoning though? We've done the math. The reasoning is because Q is greater than K. So then in part D, they tell us that K for this reaction, Kp is 8.3 times 10 to the minus third, so it's a new reaction. And they want us to just get the Ks for this reaction and this reaction, parts 1 and 2. So make sure you write this down. You got to make sure you know this, is that you add deltas, which we don't have any deltas here, and we multiply Ks. So what I need to do is I need to say, okay, well, let's look at reaction number 1 here. That looks an awful lot like this reaction that they gave us, but it looks like it's just the reverse reaction. So on D part 1, I'm going to take the reverse reaction, which that's going to be 1 over K, or the reciprocal. So I'm going to take 1 divided by 8.33 times 10 to the minus third, and that's going to give me 1.20 times 10 to the minus second. Now in part 2, what we have is this looks a lot like the first reaction, but we've got some other stuff. It looks like this is the regular first reaction, so I'm going to call this reaction 1, and nitrogen and hydrogen are on the left. They're still on the left, so we're good. So I'm going to say K1, which that reaction was 3.1 times 10 to the minus 4. And then it looks like they've added in this reaction, but they've doubled it. So I'll call this K2. So we'll take K1 times K2, but K2 is doubled. When we double with K's, we really will square it. So times 8.3 times 10 to the minus third, and we'll square that. So 8.3 times 10 to the minus third, we'll square that, times 3.1 times 10 to the minus 4, and I'm going to put it into scientific notation. I get 2.14 times 10 to the minus 8. Okay, so let's look at another K question, a free response question. Here, we've got a decomposition reaction, so delta H for this reaction, because we're just breaking things, should be positive because it takes heat to break bonds. And what we have is we've got a 3.4 gram sample of H2S. We're introducing it into a 1.25 liter container, and the container is sealed, and then we will be at a temperature of 483 Kelvin. And at equilibrium, we get 3.72 times 10 to the minus 2 moles of S2. So we will definitely have to worry about those in a second. But let's first, because I didn't give you so many lines, I'm going to write the K expression here. They don't ask for Kp. They very well could have, because we're given all gases, but they don't, so they just ask for Kc. So we'll say brackets H2 squared times S2 divided by H2S squared. And they want us to calculate the equilibrium concentration in molarity of the following gases in the container. So what I want to make sure that I do is, this sounds a lot like a rice table, so I'm going to write my reaction down here, and I'm going to see what I can figure out. You only plug into a rice table molarities or pressure. Because we're using Kc, we're going to need to do molarities. So what I need to do is I need to get the initial molarity of H2S, and that is going to be 3.40 grams of H2S. There are 34.08 grams of H2S for every 1 mole of H2S. So this gives me about 0.1 moles of H2S, but I can't plug in moles, it's got to be liters. Well, they tell us that it's 1.25 liters, and so what this gives me is 0.1 divided by 1.25, approximately 0.08 molar for H2S. Okay, so 0.08 molar. We have 0 for the initial. This will be minus x, is what a lot of people will say, but you've got to make sure you you look at the coefficient. So minus 2x plus 2x and plus x, 0.80 minus 2x, 2x, and x. So the equilibrium concentration of H2, that looks like that'll be 2x. And the equilibrium concentration of S2 will just be x. Well, I need to figure out what x is. Okay, I don't have a k value. I know that because I didn't see one, and then I've also kind of read ahead and I see that we're going to solve for k. So there must be a clue as to what x is. Well, that clue is that at equilibrium, S2 is 3.72 times 10 to the minus 2. So x is not 3.72 times 10 to the minus 2. That's what a lot of people would say. We got to divide it by the 1.25 liters. So you can see how they can set up a question where a lot of people who kind of know what's going on would say 3.72 times 10 to the minus 2, and they'd go with it, but that's not the right answer. So I got to plug in 3.72 times 10 to the minus 2 divided by 1.25. That gives me 2.976 times 10 to the minus 2. So, and I just did this wrong, H2S is not x. H2S is 0.08 minus 2x. Goodness. Okay, but I corrected myself, so I'm good. So, what I can do is I can take 2 times x. X we have now solved as 0.02976. So 2 times 0.02976. That gives me 5.952 times 10 to the minus 2. And then I can take 0.08 0.08 minus 2 times 0.02976. So that's going to end up being 0.08 minus 2 times 0.02976. And that gives me 2.048 times 10 to the minus 2. So I've solved this guy, I've solved this guy. I need to calculate the K value. Well, K is equal to H2 squared times S2 divided by H2S squared. So that equals, I know the equilibrium concentration of everything now. That equals H2, which we just said was 5.952 times 10 to the minus 2. We'll square that times S2, which is 2.976 times 10 to the minus 2, divided by H2S. We figured out H2S is 2.048 times 10 to the minus 2. And when we do that, we plug this into your calculator. I get 1.43 times 10 to the minus 4 as my K value. So C is done. And then what they ask in part D is they say calculate the pressure of S2. Well, a good way to solve for pressure would be to do PV equals nRT. So we'll get the pressure of S2. The volume is still 1.25 liters. They say that it is a rigid 1.25 liter container. Rigid means that the volume will not change. We know the moles of S2. They gave that to us. That is 3.72 times 10 to the minus 2. R is 0.0821 ATMs times liters divided by moles times Kelvin. And the temperature, what was the temperature at? It was kind of warm. It was at 483 Kelvin. When I solve for the pressure of S2, I know it's going to be in atmospheres, and I get a reasonable answer, 1.18 ATMs. And then in part E, and this will be the last part, and then I'll make a second video for the rest of this because this is about halfway through this packet. We've got this reaction, H2 plus 1/2 S2 goes to H2S. That is the same reaction, but it's flipped and it's halved. Okay, so what we have to do is get K for this. So if we flip K, or if we flip the reaction, that'll be 1 over K. And then if we half it, that'll always go to the exponent. So we get 1 over K to the 1/2, or mathematically that is the same thing as K to the minus 1/2. And so when I take 1 divided by 1.43 times 10 to the minus 4, I get 83.6, which should make sense. If the reaction is non-spontaneous in one direction, if I flip it, it should be spontaneous in the other direction, and that is what I see.